is going to help you hopefully remember where we left class. Last time we were talking about area under a curve. We were estimating area under the curve, and then we got to this really nice calculus notation. And we need to recall that this right here represents the exact area under whatever curve it is. In this case, it's your velocity curve. So take that back even further, and if we're taking some sort of velocity and we're doing area under, let's simplify it to a rectangle, and then we've got velocity measurements, which are some units per time, times a time measurement. The time cancels out, and we're really finding accumulated distance traveled over some time. So in this case, from 0 to 18 seconds or minutes, I'm not looking at the seconds or the time units here. We're finding the amount of the number of meters that were traveled in 18 seconds based on this particular velocity curve. So what I want you to think right now is that integral symbol gives you, or represents exact area under the curve. So we're going to estimate, is what they're asking us to do, is estimate in this problem. So estimate the area, because that's the best we can do, because I gave you a nice way to do it in your calculator, but that's only if we have an explicit function. We don't have an explicit function. We have specific data points, and that's it. So we can generalize what's happening, but we don't know exactly what's happening. So they say left Riemann sum of 6 subintervals. So basically, here's what I'm thinking. I'm going to be adding up 6 rectangles. So my integral from 0 to 18 of my velocity function, dt, is my area under the curve. So I'm going to estimate that by doing 6 rectangles. So I'm going to have my width times my first value. So that's going to be my velocity, since we're talking about velocity at 0. Because it's the left, I'm going to start with the left one. So velocity at 0 times my width. Notice that your width for each one of these from x to x value is 3 units of 3 seconds in this case. So I'm going up by 3 seconds. That means that my width is going to be 3 seconds. I'll draw you another picture in a second here. Then I'm going to do my velocity at, velocity at 3 seconds times the width of 3, plus velocity at 6 seconds times the width of 3, plus a velocity at 9 seconds times a width of 3. Make sure it looks like 8 times. And I'm getting close, plus velocity at 12 times 3. Getting really close, plus velocity at 15 times 3. And notice the last one is 18. I'm not going to end up using that. So let's just bump this down since I ran out of room here. And what I wanted to do is give you a quick little visual. So let's just go ahead and draw a sketch of what this function looks like for my time units: 3, 6, 9, 12, 15, and 18. And then if we take our y values, let's see, it looks like we go up to about 3. So let's go 1, 2, 3. And I'm just estimating right now. Let's do that last one a little bit higher. And then this first value, 2.3, means at 0. So when x is 0, time is 0. This is my time axis. My velocity, so maybe it helps to say this is my velocity with respect to time, and here's my time axis. My velocity is going to be 2.3, which is, I don't know, something like here. And then 2.7 is at 3, so 2.7, well, that's even higher. That's somewhere about there. And then at 6, 2.0, exactly at 2. So this first rectangle, this is my rectangle. I've got base times height. Other way around. I guess I've got height times base. My base is 3 units, that's this part right here, and then my height is based on the velocity at 0, which is 2.3. So that becomes 2.3 times 3. 3 being my width. And then I can picture that I'm actually making a rectangle right there. Then I'm going to go at 3, and I'm going to use that height for my next rectangle. So that becomes velocity at 3 is 2.7, what we had right here. And then I'm multiplying that times 3, and I'm adding that to it. And if you, whoops, trying to get rid of these. If I move these over, get those out of there. And if you make one nice string of all of your 6 rectangles that you're adding up, you can keep going plugging in your y values. The only one you're not going to use is this 18. So you're not going to use that 2.1 because when it gets all said and done, that last one, 9, is at 1.3. So it's going to be here, 1.0 is at 12, 1.7 at 15. And then in 18, my y value is 2.1, which is all the way up here, but that's not going to help because I'm not going to, that's the one I'm ignoring. I'm not going to base any of my rectangle heights off of it. When you get to the second part of this question, or I guess the third part, part C, where they say write Riemann sum, then you're going to, I'm going to draw it in blue. Actually, let's use purple for this. I'm going to draw it in purple. You would be starting with this height and doing your first rectangle off of the right-hand height. And then off of the height here, you'd be doing your second rectangle, and then your rectangle here, and so forth. Hopefully that helps you at least get started with this problem. You don't have to have even widths. With the first one you do, when you get to the back side, number 3, you don't have to have even widths for your rectangles, so that one's going to look a little bit different. But just draw it out and picture it, I think, would help for you to see what you're doing. You're just calculating the area of rectangles.